Welcome to a lesson with Dr. Powell. In this video, we're going to look at an example of finding the volume of a solid formed by rotating a region around a given line or axis of rotation using the cylindrical shell method. First of all, we understand what the line is. The line is x equals 2, and we're rotating a region which is given right here between y equals 3x minus 2 and y equals x squared. Now, if that's all we were given, we gotta kind of know where the intersections are. So we think, well, wherever it intersects, the y values are going to be the same. And the y values in terms of x are 3x minus 2 and x squared. So this is like you equate the two y values, then you find the, and in doing so, you're assuming that this x is the same for both y values. So solving for x will give you the same x value, that will give you the same y value, a point of intersection. We're going to find 2, because when we set this equal, we can bring things over to the other side, get a quadratic, which we can factor in this case, and notice that get x is 1 and x is 2 satisfy this equation. All right, so we know our points of intersection are going to be at, so right here, this is going to be at x is 1 and x is 2. That's kind of nice. It comes right to there as it's actually drawn. Now for the shell method, we first think about if we put lines that are parallel or perpendicular to this axis of rotation, which one of those is going to produce, when we rotate that one line around the axis, a shell, a cylindrical shell. Like, think of a cylinder, and the shell would be the lateral, or kind of like if you erase the top and the bottom and you just thought about the side, kind of that. Well, let's think. If you have a line in the region that's perpendicular like this, what happens when I rotate it around? Well, if we rotate it around, around the whole thing, we're going to end up getting, think of this as being flat, okay? It looks like it's like a flat washer is what we're going to get, and that's not what we're after. So, that's not what we want. So we're going to need to do so lines that are perpendicular don't work, but lines that are parallel should. And if you think about it, if we were to draw a line like this down and rotate it around, well, didn't do the best job there in that picture, but you get the idea. It's going to create a cylindrical shell. Okay. And, all right, we're going to think about volume growth with respect to radius, or radial growth, out from the axis of rotation. So if you start at the axis of rotation and you go, so think about as you're building the shape outwardly like this. So maybe at a particular, like at the radius of 0, so if you're right at the on the axis, there's going to be no volume. But as the radius gets larger and you go outward, like maybe at one point close by, the rotated region on the outside might look a little bit like this, kind of like a circus tent, but the inside's kind of fluffed like that, kind of as it rotates it around. But the question is, with respect to radial growth going outward, what is the derivative of the radial growth? The derivative of the radial growth is the area. So the derivative of volume with respect to radius is the area of the forefront of the growth, right on the outside of it, right here, as you wrap around, like what's touching that particular radius value. So that is a cylindrical shell going around. So the area of that cylindrical shell is actually equal to v prime of r with respect to radial growth. Now, as you go all the way outward to a radius of 1, so thinking about volume as a function of radius, v of 1 is equal to the volume that we're after. But noticing that v of 2, or v of 0 of 0 radius is equal to, right here, is equal to 0, then actually we can express the total volume as v of 1 minus v of 0, or as an integral, right? As the radius goes from 0 to 1, a radius of 0, so this is radius of 0 here, outwardly to a radius of 1, right? V prime of, so we can have this integral would be equal to it. Now, the problem with this is that it's not expressed in what we have here. Everything's in terms of x's. Little change of variable is an order, a substitution, if we will, between the variables. If we think about, so r goes from 0 to 1, is the same thing as x going from 2 to 1. And here, notice that x is equal to 2 minus r. So if we were to switch things around, like think of x as being like a u or something like that, and r as being like our starting variable, then to switch this to a dx is the same thing as, so if you switch it to dx, then you'd better divide by the derivative. So to switch it to a dx, you need to divide by the derivative of x, or it would be like your u, right? Derivative of u with respect to r, which is a negative 1. Okay, so then we're going to have, then we're going to get v prime of r in terms of x, and maybe I'll write it like this, if you will. But then realize what's happening. X is going from 2 to 1. But you see that negative? Because that negative, then that backwards interval from 2 to 1, we can actually write this as an interval from 1 to 2 positively, and just think of it, and then we just get this v prime of x. Noticing what this is equal to this, it's the same thing, but it's equal to the just in terms of another variable as input, so we can do it in terms of x. It's equal to the area of that cylindrical shell. So the area of that cylindrical shell, right there, what is it at that particular x value, at this x point? Well, if we take this and we were to cut it and unravel it, like, take some scissors right here and just kind of just unroll that piece and look at the area of that, what would happen? Well, we need the height. What's the height? Let's think. What's the we got to think of a number line here. The y position, a y position here, a y position here, and the difference of those is going to be the length of this, or the height of this. The height of this right here. So in order to get that height, to get this y value right here, we're going to do it all in terms of x. So this y value at x is going to be 3x minus 2. So that's going to be, so this point right here is going to be y equals 3x minus 2. And this right here is going to be y equals, so at this particular x value, this is y equals x squared. So it's going to be y equals x squared. And so that distance right there is going to be that y value subtracted that one. So we can get the height right here as being 3x minus 2 minus an x squared. And then we think about, so we have the height of this rectangle. And then to get this length right here, we think of the circumference of, like these tops and bottoms of this cylinder right here. How do you get that circumference? We got to have the radius right here. And we're going to be thinking 2 pi r for that radius, or the radius right there. So what's the radius right there in terms of x? Well, actually, we have it right here. Radius in terms of x is just 2 minus x. You can kind of think, okay, the x value right here is 2, and then the x value here, so you have 2 minus x is the radius. And then, so that radius right there is 2 minus x, and then you just simply take 2 minus x as the radius and think 2 pi times that. So we get 2 pi times 2 minus x. So that is the length right there, and that is the height right there. You multiply those two guys together, we'll get 2 pi times 2 minus x right there times this. Yeah, 3 so 3, and we can rewrite that as negative x squared plus 3x minus 2. So you multiply, so 2 pi times the, 2 pi times, so that's the circumference, but then times the height, and then you're taking an integral as x goes from 1 to 2 dx. And it's a fairly simple integral at this point, and I'll let the viewer finish this out. But at least we have successfully written an integral that will compute the volume of this region rotated about this axis using the cylindrical shell method. Thanks for watching.